nanti antes dile, ¿no?
Está bien nomás.
Hope you can see this slide. Today about understanding entropy. Okay. So here, if we take a line of data here, line of data, let's say P as 1.5. P as 1.5. Yeah. You may realize that here the SFG, so I will take only this one, SFG and HFG here, SFG and HFG. Yeah. SFG. SFG. And if you take HFG, and if you take HFG, this HFG divided by the corresponding temperature in kelvins, okay, corresponding temperature in kelvins, T in Kelvin, T in kelvins. Example, if you calculate here, this is same as HFG value here is 2226 kilojoule per kilogram divided by temperature in kelvins. So what is that? Temperature is 111.4 plus 273.4. So this is SFG. Can someone calculate this? Can someone calculate this? Okay, can someone calculate this? See what's the value of this. See what's the value of this. 2226 divided by 111.4 plus 273.4. 2226 that is 5.7848. 5.7848 5.78.48. Okay, let's say 5.785. 5 point. Yeah. So you have to, here 273.15, if I'm not mistaken, let's see. 273.15. Yeah, if it is 273.15, let me calculate this. Yeah, 5.788584. 5.788584. 273.15. Yeah? 5.788. Yeah. So this is, yeah, 788. So this is to the nearest three decimals, this should be 789. Because 5.7885. So 5.7885 is 5.789. So it is exactly the same. I think last week also I mistakenly used 273.4, but it should be 273.145 something or 273.15. So you should realize here that in this saturated steam table, whatever the pressure line here for constant pressure, this SFG is equal to HFG by T in kelvins. Okay, so this is just an example only. So if we take 1.5, if you take 1, again you can see the same and exactly the same result. So what's the meaning of this? How come exactly the entropy increase when liquid turn into vapor form, the entropy increase, the increase in that system equal to HFG by TK. What is this? Yeah. So we are going to explore that now. Okay. So we know that SFG, the entropy is a calculated property, but what is this? So that is the point we should learn now. Okay. That's the point. Also, while we are sharing this, you should read your textbooks and text notes I passed to you all. You should go through that. So I'm sharing some other things also relevant to thermodynamics. Okay. So let's say in this experiment, let's say how you are conducting this experiment, the constant pressure experiment, how you are going to conduct this. Yeah, we have to understand that first, how you are going to conduct this experiment. Okay. So I'm going to take this out. I put it in a very smaller scale, just for you to see how you are going to do this experiment. What kind of experiment is this? Yeah. So this is something like a constant pressure, heat addition to water. Okay. So you have something like a chamber. You have something like a chamber. Let's say this is the chamber with the wall. Okay. Chamber with the wall here. Chamber with the wall. Chamber with the wall, and here you have the water here. Okay, you have some water here initially with some water. And the balance. The water I just put here. Yeah, water. Let me take instead of this. I just draw a line here. You have some water. And the balance there should be some steam. Steam. Okay, something like this. Yeah, something like this. Yeah. Okay, water and steam. So here is water, and here you can see some steam, and there should be a moving cylinder. Sorry, piston here. Okay, this is a moving piston. Yeah. So this is a moving piston. This is a moving piston. So uh, the reason is to have a moving piston is you have to maintain the pressure same as 1.5 bar. So here the pressure is 1.5 bar. Okay, so you have to maintain the same pressure. The maintaining the same pressure is done by putting a weight here on top. Putting a weight here on top. Okay, you put a weight here. So weight just to match 1.5 bar. Okay, a weight just to match 1.5 bar. And this is sealed but no friction. Frictionless piston. Fully sealed this water steam enclosure. Okay, like this. So then how you are going to increase the vapor here in this vapor liquid form. Okay, so initially you have vapor like liquid like this, a big portion, but later your liquid becomes less and the volume of the gas or vapor become more and the piston moves up. So that is how it is. Piston moves up. Okay, and the pressure remains as 1.5 bar. So here, this is a constant pressure heat addition. So you are adding some heat here. Okay, you are adding some heat here to the system. You are adding some heat. Let's say this is how you are adding heat. You are adding heat. Okay, so let's say, so when you initially zero amount of vapor, initially 100% water, and finally 100% vapor. So that's how the situation is. Okay, so initially you have the 100% water, only this. Okay, only this, but you have 1.5 bar pressure here. Water only 1.5 bar. You just start heating up this. Okay, then what happens is slowly, let's say I will put it here. Yes, so this is the initial. So you just started heating up. So after some time you can see same 1.5 bar, but now this piston moves a bit. Okay, piston moves a bit, and you have water a certain amount, not the same, but it's a lesser amount. Okay, and further what happens is, yeah, this one. So when you continue heating, there comes a time, a moment, your last water droplet evaporates. Last water droplet evaporates, and your pressure maintains and the volume sure increase. Okay, volume sure increase. Yeah, volume sure increase. The gas volume sure increase. Yeah. So that's how I say it is. Okay. So here the 1.5 bar, last water droplet just evaporated. Just evaporated the last water droplet. Okay. Just evaporated. This one we call, yeah, just evaporated. Okay, just evaporated means if you take a little heat out, last water droplet will form again. Okay, if you take little heat out, the last water droplet will again form. So this is a very slow heating process. So your pressure remains constant and your volume changes. So pressure is maintained by this kind of, let's say, frictionless piston here. So the when the gas or vapor needs space, the piston lifts. So this is slow heat addition. It's a very slow heat addition. Okay, this is a very slow heat addition. So I'll leave it here. This is a very slow heat addition. Okay, yeah. Kilojoule per kilogram per Kelvin is the unit here for the entropy increase. So let's say now from here to here, the here is just 1.5 bar. The last water drop evaporates. Here, 1.5 bar. The very first water drop. Okay. The first water drop just evaporated or about to evaporate. First water drop just evaporate or about to evaporate. Evaporate. It's about to turn into gas. Last water drop, let's say, just evaporated or about to evaporate. Both are okay. Yeah. So here, there will be a time span taken for this. Okay, you just follow this one-time learning. There will be a time span for this. Time span from here to here. There There will be a very longer time span, not immediate, very longer time span. Okay, quite large. So this is a longer time span and slow heat addition. Okay, very slow, extremely slow. Slow heat addition, extremely slow heat addition. Okay, and takes or took quite longer time. You can manage this in laboratory. So these are lab scale experiments. So accuracy is there. So extremely slow heat addition. Okay. How can you make this extremely slow heat addition? How is it possible? Okay. How is it possible to have extremely slow heat addition? Okay. How is it possible? You know that for heat addition, there should be a temperature difference. Okay. There should be a temperature difference. We call it delta T. Okay. We call it delta T. Delta T. So delta T here, add the heat transfer from the surface to water. This delta T is very small. Okay, I just move this a little bit. Show you delta T here. So here delta T is extremely small. Okay, so very small delta T. Here at the heat transfer. Okay, delta T. I just mark it to make it more visible. This delta T is almost zero, means is very close to zero, but not zero. Okay, so small delta T, very small delta T. So delta T is very small. It is something like 0 plus, sorry, 0 plus, 0 plus. Okay, it is something like 0 plus. Delta T, something like 0 plus. Yeah, you can see it. Delta T is very small. So when you have a very small delta T here, when you have a very small delta T, extremely small, so this is a very slow heat addition, extremely slow heat addition, takes longer time. Okay, delta T is almost zero. Not to say zero, there should be a temperature gradient, temperature difference, but this is very small. Okay, this is extremely small delta T. Yes, extremely small delta T. So slowly, gradually, slowly, from the state 1, okay, from the state 1, from the state 1, to the final state. The best is to say this is the gas. Okay, this is liquid. Liquid, saturated with gas. Okay, but liquid, this is the saturated we call. Okay, and this gas here also we call saturated. Okay, fully gas but saturated. Okay, fully liquid but saturated. Okay, so here in between 1 and 2, liquid and gas together, we call this is in equilibrium. Equilibrium. Okay, so in the equilibrium what happens is any moment if a liquid molecule moves to the gas phase, the gas molecule will come down to the liquid phase. So that is what is equilibrium. So very slow heating, otherwise continuous heating, of course, more liquid turns into gas, but here liquid gas in equilibrium at any time. So this is the lab experiment, okay? So this is the lab experiment, okay? Okay, this is the lab experiment. So you imagine at 1.5 bar, when you have that very slow, extremely slow heat addition with small temperature differential here, for longer period of time it has to be, because still here extremely slow heat addition, you have to have a certain quantity of heat to be added. Okay, heat to be added, and then the liquid turns all into gas here at the saturation condition. So this change start from liquid saturated, change to gas saturated. A bigger volume is there now. Finally, the fully gas. Initially, it is fully liquid. In between, liquid plus gas in equilibrium. Okay. So this is the laboratory scale, the experiment, and based on this experiment, the data gathered are represented or are found in this table. Okay, so here you can see the heat addition here from turning F means a fluid, liquid, to gas. So let's say we call this the heat requirement. Let's say this is Q. Q, the heat requirement from liquid to gas. Okay, that is same as the increase in H, or the enthalpy here for this case. QFG is HFG. That's the situation, okay? And actually SFG, not to say SFG, not to say HFG by TK, but SFG is QFG by TK when this is in, how to say, when this is in equilibrium. So all the while following equilibrium process, it's an equilibrium. Liquid plus gas all the while. Gas. Equilibrium, liquid plus gas. And we call this also reversible. Reversible. So we have to learn what reversible means also. We have to learn what reversible means. So the reversible processes are very slow processes and no friction involved. That's why this piston is frictionless piston. Okay, here, reversible. So your piston is frictionless. That's also very important. Reversible with frictionless piston and small or smaller what delta T temperature gradient. Okay, smaller delta T temperature gradient to temperature difference. So this is the experimental setup. Generally, this is the experimental setup must have for this generation of data. So equilibrium liquid plus gas, reversible with frictionless piston and smaller delta T. Okay, so in this experiment, okay, when you have this reversible experiment with reversibility, SFG is QF by T or QFG by TK. So that is very important. Okay, SFG is not HFG by TK but QFG by TK. The heat addition divided by the temperature here inside the system. Okay, the temperature is T in Kelvin. Okay, T in Kelvin is the temperature. Okay, temperature is T in Kelvin. That is very important. So you have a certain temperature, Tk. Yeah. So you divide this QFG by this Tk. Tk for this case is T in Celsius is 111.4 plus 273.15 is Tk. So this is the Tk value. Okay, this is the Tk value. Okay, your Tk is 111.4 plus 273.15 in Kelvin. Okay, Kelvin. So this is a very important slide. You should note that if there is a moving part, so in this system, there is a moving piston, means that to adjust the volume by expanding the liquid when turning to gas, okay? To adjust the volume, you have to have the variable system volume, and that is achieved by moving this frictionless piston upward when you are putting energy into the system. Okay, so this QFG is the system, the energy needed, the heat, into the system. So QFG by TK, the temperature here in the system is the entropy. Okay, so here this is the entropy increase or the entropy received by the system because of this heat input of QFG. I hope you can understand very well this. Okay, I hope you can understand this very well. Okay, so this is the one way of understanding the entropy definition. Okay, so here now the steam table, the property table help for this. Any question? Any question? Okay, yeah, let me move to the next slide. It's the same slide I take. It's the same slide. Understanding entropy. Same slide. So you have this bit. Yeah, interesting. So this initial, the final, and a general stage in between are shown here with this three. So this is the starting of the heat here at the liquid saturated condition. This is the final heat input. In between, continuously applying heat input. The total become QFG. Okay, so that is very important. Okay. Also, we can say instead of FG, if the first state is 1, the final is 2, you can have Q12 also here. No issue. Okay, Q12 also no issue. Okay, so this is the one. So now here I take this SFG as HFG by TK. It happened, but not this now. SFG should be QFG by TK. So this is equilibrium liquid and gas all the while, and reversible and with frictionless piston. Okay, yeah. So you will see this one, and also smaller delta T, smaller delta T. So this is the situation. Okay, yeah. And now what happens is TK is this much. Yeah. Based on the experiment, we can see that. I'm rewriting it. QFG is HFG. That's why. So the HFG by TK is not SFG, but SFG is QF by TK, QFG by TK. That is HFG by TK, because here in this case, QFG is HFG. So that is the reason. QFG is HFG. For this experiment, okay? For this experiment, QFG is HFG. That's why. So QFG by TK become HFG by TK. Okay? Because QFG is HFG. No other reason. QFG by HFG. Good. Okay. So this is how you should say this. Okay. SFG is QFG by TK. Okay. TK, and this is for equilibrium condition. Yeah. So that is very important. Yeah. This is for equilibrium condition. Okay. Yeah. I hope you can understand this. So let me work with the other slide. So here, I will take this yes, since it's a good introduction for the memory. So here, SFG is QFG by TK. And we have to add another wordings here. Equilibrium or reversible. Okay, reversible. Okay, so another word here, the reversible appears. Okay, so later I will explain what reversible is. Okay, yeah. So SFG is QFG by TK, equilibrium or reversible. Actually, this equilibrium is there because of reversible. Reversible word is here. Okay, equilibrium, liquid plus gas all the while. Okay, yeah. Equilibrium, liquid plus gas, and reversible. Okay, so reversible means, so I will take this, reversible means reversible with frictionless piston, okay, and with smaller delta T, okay. Frictionless piston means if there are a piston with the friction, it affects the system, okay, and with smaller delta T, okay, means this is something like this heat transfer is reversible, which means if you add little heat, same way if you reverse the heat, it will come back to the previous original position. That is the uh, phenomena we are considering with the smaller delta T, okay, with the smaller delta T. So if there is a friction, what happens is when your Q or the heat reverse, piston may remains there. So then the system is different. Now you can understand. If you take the heat out, piston may remain there if there is a friction on the piston. So the system is different. So it won't come to the previous state. Okay. So the frictionless and smaller heat transfer, the delta T, that is very important. Okay. Yeah, with smaller delta T. Yeah. Very good. And Tk means the T in Kelvin, T of the system or the wall here, the heat transfer here, T in Kelvins, okay? Tk in Kelvins. Tk in Kelvin, okay? Tk in Kelvin. So here for this case, SFG is QFG by Tk equals HFG by Tk because QFG is HFG, okay? Because of this. Yeah, QFG is HFG.
Excuse me, sir.
Yeah,
So what is the meaning of QFG?
QFG, yeah. QFG is the heat addition to this liquid. So finally, there will be vapor formation and the liquid and vapor together is here. So the QFG is from the initial fully liquid, we call it F, to fully gas, G, gas saturated. So turn this liquid into gas at 1.5 bar pressure. The heat required is QFG. Okay,
Okay, sir.
yeah,
Okay.
QFG. Okay, thank you. Thank you. QFG is the heat requirement. Yeah, heat QFG. Very good. Heat QFG. Okay, heat QFG. Yeah. So that is the heat. So entropy is heat divided by temperature at equilibrium. Okay, yeah. But for this case, it is only for this laboratory scale specific test. Even for test data, it is like this. Okay, good. Now, so I'm saving this and I'm going for a new slide here, duplicate slide. Now you see here, this is for sake of memory, where we got this, okay? And we have the SFG as QFG by TK, okay, equilibrium and also reversible. QFG is the heat, okay? So I'm going to have a generalize from this, I'm going to have a generalized entropy increase. Okay. For the previous case, this entropy increase means SFG. Okay. Is equal to heat transferred. Okay. Heat transferred divided by, I would put TK. Entropy increases. Heat transfer divided by TK reversible. Okay, reversible. That is very important. So let's see how I'm going to rewrite this. TK reversible. Okay. Entropy increase. Same like the previous. So in the previous case, so what happens is this QFG is the heat transfer. Okay, divided by TK. TK is the temperature in Kelvin. Okay, from the previous case. See? So the previous case, entropy increase is SFG. Okay. And previous.
So entropy increase or decrease, no?
Here. Here the heat transfer to the system. Okay. Heat transfer to the system. Yeah, heat transfer to the
So
system.
it can be decreased, or no?
Yeah, there is
Yeah.
a possibility for decrease if the heat is out from the system.
Okay, sir. Okay.
Okay. Now heat is into the system. So when heat is into the system, there is an entropy increase. Very good, Bhutan. You should clear this. You should get this clear. You should ask the question. That is very important. That's why I'm doing this step by step, slowly for you to digest. So now heat transferred is QFG, heat transferred to the system. Okay, so our system is the system we are seeing here, trapped in between the moving piston and the cylinder like this. Here you can see initially liquid about to evaporate. So liquid being evaporated and more gas volume. Finally, the third is here the last drop of water just evaporated. Means if you reverse the heat, that water droplet, that steam, that water turned into steam again back to as water, and the piston moves a bit down correspondingly because there is no friction. If there is a friction, we have issues. Okay? Yeah, because it won't reverse back to the same. That's why reversibility means once you reverse the process, so here it's the heat addition. When you reverse the heat, now is from outside to towards the system. So if you reverse the heat outward as outward the system, so the volume becomes reduced. the gas turns into water droplets and piston moves down and pressure remains the same as 1.5. Okay, that's fine. So here the point is the reversibility. Okay, reversibility. And when the system is reversible, and since this is liquid and vapor, this system is naturally vapor liquid in equilibrium. Okay, but here for us, the important is the reversible. Okay, so that's good here. So let me duplicate this slide again, and then I will make a snapshot here. Remove this. I put the snapshot. You have one more here. Whenever you can make it big. Okay. So this is the history. And finally, entropy increase here, the heat transferred. Okay, to the system. Okay, to the system. Towards the system. Okay. Now that is QFG divided by TK. Okay, divided by TK, heat transfer to the system. Yeah, to the system. Anyway, I will take this out because it jumped to the other line. Heat transferred to the system. So here I will put here in the system. In the system of vapor. Liquid enclosure. Okay, we call this vapor liquid enclosure. The system of vapor liquid enclosure. So this is the vapor liquid enclosure. Okay, so that is reversible. So entropy increase become this. Yeah, entropy increase become this. Okay, very interesting. And the other issue is liquid entropy is this. So I will rewrite this. I will rewrite this vapor liquid enclosure. If reversible, entropy increases heat transfer divided by Tk. So I took this reversible subscript out. Okay. Yes. If reversible, if reversible, okay, if reversible. So every time I put as reversible within brackets, so I put here, if reversible. Yeah, very interesting. Okay, entropy increases. Heat transfer divided by Tk. So here is SFG by Tk. So what I will do is entropy increase. Instead of entropy increase here, I put delta S. it's okay to put delta S. Delta S. Okay. Heat transfer Q. Instead of Fg, I put maybe 1 to 2, Q12 by Tk. Okay, 1 is initial state, state 1 to final state 2. Okay, so now Q12. So you know Tk, Tk is the constant temperature there I put. That is in Kelvins, okay, system temperature. If reversible, initial state 1 to final state 2. So heat addition from 1 to 2 by Tk is the delta S. Even here I can put 1, 2. That is okay. Delta S 1, 2. Okay. Tk. T is a constant here, T1, 2. Otherwise you have to go for the integration. Yeah. So just put here Tk1, 2. Okay. I believe you have a little bit more familiarity now. So yeah, if you have any question, please raise the question because otherwise it's difficult to later digest this. So this helps you to look into more literature on entropy. But this is the best case we can understand because we are really referring the steam table. So we can rely on steam table. So there is no any hidden things. So steam table, when we take QFG as HFG divided by TK, it will be SFG exactly. So that's a reference, okay? That's why I'm always using steam table to prove the concept or show the concept of entropy increase. Okay? Entropy, we always consider either can be an increase or can be a decrease. So that is the entropy change. Okay, delta is 1, 2. Okay, good. So delta is 1, 2 is heat transfer divided by Q1. So very good. And let me copy a slide here. So now this is generalized one, understanding entropy. So I take all out here, nothing to do with 1.5 bar. This is about understanding entropy. So this is the state 1. State 1, I'll put it as 1. Okay. This is 2. I'm working here with no much of lighting. This is 1 to 2. Okay. This is 1 to 2. Okay. This represents 1 to 2. Very nice. Okay. So no this. No this. No HFT. Q1 to 2. heat applied Q1. This. Okay. Still applicable. Extremely slow heat addition took quite longer time from state change from 1 to 2. Okay, state change from 1 to 2. Very interesting. Take this line out. Okay. So now this is S12 is Q12 by Tk. Very interesting. Okay. Reversible with frictionless piston at tip and with smaller delta T. Very nice. Okay. And Tk is in Kelvin, the system temperature. Kelvin, the system temperature. At heat transfer. Surface, let's see. Surface or interface. At heat transfer interface. So here it's Tk. So the delta T also, delta T also at the interface. That's why I put this at the interface. Okay, at the interface, you are considering delta T. Very nice. Later we can understand some more, don't we? This is the accumulation, the total of Q. I made it a big Q. Okay, heat Q. Heat supply to the system. Okay, Q2K is this. So still I can keep this example. Example. This is saturated water and steam at 1.5 bar. Okay, so that's a case. So you have some understanding of this. Understanding entropy. Okay, very interesting. I'm going for another slide. Now, the situation, let's say, not reversible. With friction piston, with not to say small, a significant delta T. Okay, Tk can be the same. Now what will happen is no more this is equal. Okay, no more this is equal. So that is the situation. No more that is equal. Now what happens is S12 is bigger than Q12 by Tk. Yeah, okay. S12 is bigger than Q12 by Tk. So the best written is here. Q12 by Tk is bigger than Q12 by Tk. I would write here it is as S12 is bigger than Q12 by Tk. When Q12 by Tk is reversible. So this is S12 reversible. Okay, S12 is bigger than S12 reversible. Yes, this is the situation. S12 irreversible. Well, is greater than S12 reversible. So that is the situation. S12 reversible is Q12 by Tk reversible. Yeah. So when irreversible, this is the situation. Irreversible means not reversible. Okay. Or let's say I put irreversible. Irreversible means with friction piston with significant delta T. So this is the point. Okay, this is the point. For you to consider S12, the entropy increase when the system is irreversible is more than the entropy increase when the system is reversible. Okay? When the system is reversible. Yeah, means because of the friction and the significant delta T. Yeah, higher delta T and the friction issue. Frictions and the temperature differences cause the system irreversible. So this is the issue. Reversible systems are better, okay? In what? Better in what? Yeah, that's the question. Okay, better in, let's say, efficiency. What efficiency? Let's say the energy efficiency. Okay, better in efficiency. Reversible systems are better. Okay, better, much better than irreversible systems. Okay, so let me say this is better. Within bracket, I will put the efficiency. Okay, the effectiveness of the process. Yeah, reversible systems are better. Yeah, let's say if you need to have a process with reversible, if the energy interaction, let's say 100, In irreversible system, to have the same, your energy interaction is more than 100, let's say 120. Likewise, that's why. So the irreversible processes are better. So, and also low entropy systems are better. Also, reversible systems are better because of low entropy. Low or reduced entropy. We are going to discuss afterward that kind of systems. Okay, low or reduced entropy. That is very important. Okay, because of low or reduced entropy. That is very important. Reversible systems are better. So that's why in thermodynamic systems, when you design, it is more than calculations. Okay, how to make a very good system, you have to consider the minimizing of irreversibilities as well. Okay, minimizing the irreversibilities. So including friction and delta T. There should be some more. Okay, including. Okay, including. So except this, instead of this, I will say including. Including frictionless. This is yeah, reversible. I will put here. Reversible. Including frictionless and smaller delta T. What's important is the reversibility, including frictionless and delta T. Even in a flow of liquid. So if it's a laminar flow, it is more reversible. If turbulences are there, the frictions are there, and that is irreversibilities we are adding. Okay, that's why you have to learn a lot. Okay, so irreversible we can see including friction and high delta T irreversible. So now let's see, is this this one, the irreversible, where should I put? I have to look into the next slide. Okay, and I will take this snapshot. Later I can transfer this to visual notes for your reference. Even if I'm presenting this in the class, sure I will go with this in writing on the blackboard. Okay.
So irreversible system, the pressure will build up, no?
Irreversible. Yeah, pressure can be changed. Don't worry. Yeah, here not about the constant pressure. Pressure can be changed. Okay, this is for the
Okay, sir.
simple understanding. Even here the temperature can be changed as well. But for general understanding, I just put TK. Okay, Buddha. Later we will
Okay,
go for calculations. Very good. Please ask the questions. Yeah. And irreversible, I will put here. I have space here. Irreversible. This is very useful practical tips. That's how you can go for innovations if you don't know the concept of entropies. You cannot go for innovations of the systems. Yeah. So irreversible, including friction and piston or anything. Yeah, not necessarily friction piston. Yeah. Reversible means including friction free. Here free. So irreversible, including friction and higher delta T. higher delta T, irreversible including friction and higher delta T. That's why you can see in the engines and all, yeah, it's a matter of managing this friction and even the delta T's, the combustion, the temperature rises. A lot of things are there finally to optimize the things. Optimization in the sense is managing the entropy as minimum as possible. Yeah. So S1, 2. Okay. Very interesting this. So very good. And I have to go for another slide. Now you have this as a photographic memory. You have this as a photographic memory. Let's see. Wholesale, always I prefer to maintain the history on the slides. Then you feel good. Now here, yeah, you can see that S1 is greater than S12 reversible. Okay, based on this, we can come for a general expression. Yeah. Instead of S1, yeah, reversible, I will write here just S12. So I hope you will agree with this. Not completed yet. Greater than or equal. Q12 by Tk. So this is the general expression. Okay. Equal sign stands for reversibility. Equal stand for reversibility. So this is general statement. Only S1 to reversible is equal to this. This is the equality. That is S12 is equal, but when Q12 is irreversible, otherwise, yeah. S12 is greater than when Q1 by Tk is irreversible. So these two are combining and rewrite this. So first one, yeah, first is okay, and make it as a single statement. This is the one. Rewriting it, you can see below too. So we call this Clausius inequality. if I'm not mistaken. Okay, Clausius. Spelling should be okay. Let me see. Clausius equality. Clausius. Yes, okay. Clausius. Clausis. 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 Inequality of Clausius statement. SIUS. AUSIUS. USIUS. Clausius inequality. Or Clausius statement. Either one is okay. So this is the famous expression for the entropy. So here it's for a process. Initial state is 1, final state is 2. So entropy change is S1 to 2, and that is greater or equal to Q12 is the heat interaction by Tk. This is a very generalized expression. Okay? Very generalized expression. Yeah. So we have, I think we easily, step by step, we move to this level thanks to this property table. Otherwise, if I just mention this as a Clausius inequality, you will accept this because not I said, but Clausius said. But now we have a basis for this. We have realized this. Okay, we have realized this, and you should have a better understanding and some good memory on Clausius inequality. So wherever the heat transfer aspects are considered in the system designs, so now you know how to control the irreversibilities and to make the systems better. That's why you know this controlling irreversibility, it is more based on some, how to say, undocumented knowledge. Those knowledge are not documented, but those are based on experience and practices. That's why Japanese engines are more efficient than Chinese engines. For sure, and maybe for coming 10, 20, 30 years, Chinese cannot come to that level of good performing Japanese engines level when it comes to automobile technology. The reason is this entropy minimization is not maths, okay? Is not maths. It really relates with some art, manufacturing techniques, knowledge about the metals, the surface finishing, heat transfers, a lot of things, and those are not in the books. But with the people, they do it, and they never share this. But organizations, they have this knowledge, undocumented, untraceable, but valuable knowledge. And ඒක තමයි කියන්නේ දැන් ඔය in Japanese, like the countries, the automakers, when they recruit young blood like you at your age, at your level, so they let the young people to follow the seniors, and gradually in 15 to 20 years time they have that undocumented knowledge. We call it tacit knowledge. It's not in the books, but then once these young people come to that age, their positions also elevated, they are well paid, and they are highly recognized, and they will be there with the company. And then generation to generation, this practice follows. And they have plenty of knowledge accumulation. So that's the reason how the technology get matured. And no one can copy such technologies because of that practice with the maintaining and carrying forward that undocumented hidden knowledge. Yeah, that knowledge is quite personal, but this personal knowledge is shared from generation to generation, and that knowledge flows with the company and the organization. So, Vanid, that's why Forming an industry and getting a matured industry is not a 1 day game, it's not a 1 year game, it's not even a 10-year game. You have to have a very long lasting, at least 20, 30 years to get a very good, matured, world class, outstanding industries. Yeah, that's why. So you have to have the industries, we have to wait for that long. And you have to have a very good company cultures like what the 3M companies US they are doing, Toyota doing. Yeah, those company cultures, those are extremely important. That's why. So it is okay to learn this kind of thermodynamics. Very good. This basic knowledge is very important. And in return, you should look for the practical knowledge. Minimizing entropy you will not find in books, but you have to think how to minimize the entropy in the refrigeration systems, in the automobiles. Some even they modify the engine. Yeah, finally, if your performance is better and your energy saving is better, wherever there may be some entropy minimizing, you should recognize those, and those will be the technologies. Understand? That is very important. So try to capture that kind of improvements and the experiences you have done by using your work with the great interest you paid. Yeah, that is very important. The interest, attention on the work, and a little bit of knowledge on this. So anyone, even these Japanese automakers, the technologies, they may not know entropy, but they know how to reduce the entropy. That is the important thing. That's the important thing. That's why we have so many educated, qualified people, but only the papers, they are good in evaluations, but when it comes to practice, far behind. Very unfortunate, including myself. Okay, so you should make a change. You should be different. Okay, but we can. You believe Sri Lankans can? Yeah. So take these lessons, and this is more than thermodynamics. So next session, not today. It's 3:30 now. I will look into the entropy minimization, at least in cooling appliances. Refrigeration, we will start. Automobile, we will see how we can improve the minimizing of uh, entropy generation. Yeah, this kind of things. And future, it is not about the energy audit. It's about the entropy audit. Yeah. So if you learn thermodynamics and if you don't know entropy, your knowledge is something crazy, Yeah, no use. Yeah, outdated. Yeah. That's why I thought of sharing this entropy knowledge with you, but learning this is totally with you. But at least I'm reasonable to you because we use some facts and the figures and data. So based on this, we build this. Yeah. So at least we have some basis. So read about entropy. Very interesting, very useful. Yeah. Quite philosophical, but also practical. Yeah. So today I couldn't start the class in time because of some another official matter. That's why. But anyway, today we have done something quite sizable. So no time to go for examples because if I go for examples, it will take another 1 hour at least to complete an example. So let me put it into the coming week. Okay, Bhutana? Yeah. So one more thing about the workshop technology practicals. Please arrange the timing and let me know. Even this Mr. Danush from what is VTA? Yeah, workshop also called me. Somehow both of you have to arrange the timing, fix it. Fix means no more changes. And those who miss the classes may miss the courseworks assignment. So we will fail the subject. That's why before I am stepping in, better you work with mechatronics manufacturing together, the students, and check with PT and get this arranged and do it well. Don't get it repeat. For CA repeat means that is really, we cannot do anything because uh, that is documented and we are receiving the CA marks from the BTA side. That's fine. Put everybody understand? Okay. Below? Yeah.
Okay, sir.
Yeah. So be responsible on that one. So Hasita and the mechatronics are a representative, Utala. Yeah. So we serious about arranging the workshops, the practice, the continuous assessment for workshop technology, and get it done and learn about entropy. Okay. And go through the notes. Yeah. Anything, Buddha?
Can you send this presentation, sir?
Sorry.
This presentation is send this.
Okay, this one we just built over here. So I will put this right now into Google Classroom. Okay. So what's the name of this presentation? The presentation.
Entropy. Understanding entropy.
Understanding entropy is 2v2. Okay. Yeah, I will upload right now.
So what about Steam paper?
Steam table. Okay,
Yeah.
you can download. I will send it to you right now. Also Steam table.
Okay. Sir, thank you.
Also make sure you download Coolpack. Okay.
Okay.
Yeah,
Sir.
we will work on that as well. Please download Coolpack. You can find the link. If you cannot find, let me know. So I will upload this understanding entropy is 2b2n the Steam table right now. Okay, Buddha. Now let me upload it now while we are online. Save this. We have to go to Google Classrooms. Google Classroom. Let's see.
Sir, how about the last semester result?
Last semester results. Last semester results marks are there. I think we will check with our HOD, Dr. Jailal, and we will let the results out. Yeah, but of course, B2, some results yet to come, Buddha. Some results yet to come because of the COVID issues. Even some papers still we couldn't send to the lecturers because some lecturers are so far that even some are from Mathur area. Yeah, Thermodynamics.
Okay, sir.
Yeah, that's why. So you have to be patient for that. So how to upload? How to upload? Okay, add file. Add file. Add browse. Downloads. Yes, understanding entropy is 2b2. I found it. Yes. This is today notes. Today notes. What? Understanding is 2b2 and also I have to look for the downloaded. Download it. Yeah. Yeah, the things I downloaded. Anyway, I will upload the this right now. So I'm going to post this entropy one. Yeah, it's being posted now. Entropy table. Let me see. Rogers and Mayer. Yes. Rogers and Mayer. Steam tables. Yeah. Okay. Yeah, I got it. Yeah. So let me upload that also. Then it is done. File, plot, browse, download. Yes, I have Steam tables. Yeah, good. Those are not big files. 1.3. I will write this as Rogers and Mayhem. I have Steam property tables, but there are more than Steam table. Just may have, yeah. So good. I post that as well. So do you need the link for the cool pack? Can you find this link, cool pack? Cool pack. Yeah, let me find this as well. Cool pack software. Cool pack IPU. Yes. I'm uploading that as well. Cool pack. Pack link. Download. Software. Here's the link. Post that as well. So previous notes also, if we, yeah, last week note, that is Excel work, I think I didn't save it. But today, good that we worked on here. So good. But I can post the recording last week. Do you need the last week recording? Thermodynamics. Hello, students. Last week recording. Hello. I know that. Yeah. Can you hear? Okay, Buddha. All looks silent. Yeah. Okay. Let me stop the class then. Yeah, I have posted the link for cool pack download. Today, this understanding entropy PowerPoint and the Rogers and Mayhew Steam table. I almost all the three in the Google Classroom. Okay. So Google Classroom have posted. Okay, Butala. So let me stop the class now. Let me stop the class now. So good luck to you all. So see you next week if any issues. Yeah. Sure.
Thank you, sir.
Okay, thank you, sir.
Let me stop the yeah. Okay. Bye. Bye.
Thank you, sir.
Okay. Bye. Okay. Have a nice weekend.